Okay, so let's unpack this a bit. Imagine the air around you right now. It's absolutely teeming, right? With this invisible symphony of radio waves. Your phone, your Wi-Fi router, maybe that drone flying overhead, they're all humming along, broadcasting and receiving messages through this unseen network. It's a constant, incredibly complex conversation happening all around us, carrying everything from, say, your video calls to vital security data. But here's the fundamental question. How do our devices, just sitting there silently on our desks or maybe tucked into our pockets, how do they know what language these invisible waves are speaking? How do they distinguish between like a voice call, a high-definition video stream, or just a simple text message, all encoded differently and zipping through the air at the same time? That's really the core challenge we're diving into today, this crucial task of identifying the specific modulation scheme of a received signal without any prior knowledge of what it's supposed to be. It's kind of a hidden superpower, really, that's absolutely essential for modern communication.
It is, and what's truly fascinating here is just how much the complexity of these wireless systems has exploded, especially over the past few decades. We've moved so far beyond the simple, predictable patterns and, the relatively straightforward communication methods of early radio. Just think about the sheer volume of data we all consume every second, the billions of devices connected globally, and all the diverse applications, smart homes, self-driving cars, you name it, that rely on seamless wireless connectivity.
Right. It's everywhere.
Exactly. And in this incredibly congested electromagnetic spectrum, the traditional sort of rule-based approaches, well, they just can't keep up. These older methods relied on engineers painstakingly defining every possible signal characteristic.
That sounds brittle.
It is. It's like trying to manually map every single road in the world in real time while new roads are being built constantly. It's just not feasible anymore. And this is precisely where artificial intelligence, AI, steps in, offering a much more dynamic, adaptable, and frankly, remarkably efficient solution.
I like that analogy, they're constantly building new roads. It really highlights the scale of the problem we're facing. So, okay, our mission for this deep dive then is to really understand a groundbreaking new approach. We call it a multi-level approach using deep learning. It promises to be a shortcut to being well-informed on how AI is revolutionizing this thing called Automatic Modulation Classification, or AMC, in wireless communication. And our main source for today's exploration is a recent, very insightful research paper. It's from the journal Physical Communication titled Deep Multilevel Architecture for Automatic Modulation Classification by Parmar and colleagues. It seems like a piece of work that really tackles some fundamental challenges in this space with a clever, quite elegant solution.
That's right. It's all about designing intelligence that can actually keep pace with this ever-evolving wireless world we live in.
Okay, so let's truly start at square one, maybe for listeners who haven't encountered this before. Before we can appreciate how AI is classifying these signals, we really need to understand what modulation even is. In the simplest terms you can manage, how would you define it, and what exactly is this automatic modulation classification trying to do?
Right, modulation. At its core, modulation is really the art of embedding information, whether it's your voice, maybe a picture, or data from an app onto a radio wave. Think of a radio wave like a blank canvas. Modulation is a technique you use to paint your message onto that canvas.
Okay, painting onto a wave. How does that work?
Well, you can change its properties. You could change its height, its amplitude, that's like making your voice louder or softer. Or you could change its frequency, which is like shifting the pitch of a sound. Or you could change its phase, which is a bit more subtle, like altering its starting point in a cycle. Each of these changes, or combinations of them, creates a specific accent or dialect for your wireless message.
Accent or dialect, I like that.
Yeah, and different accents can carry different types of information more efficiently or maybe more securely. For instance, some modulations are fantastic for sending huge amounts of data really quickly. That's often what your Wi-Fi uses. Others are better for transmitting maybe small bits of information over very long distances or through extremely noisy environments like signals from a remote sensor somewhere.
So it's not just about blasting out a generic radio wave, it's about giving that wave a particular recognizable characteristic. So the receiver knows exactly how to interpret the message and, pull out the data that's embedded inside.
Exactly, you've nailed it. And that's precisely where Automatic Modulation Classification, AMC, comes into play. It's the sophisticated task of automatically figuring out what accent or dialect a received signal is using, purely from analyzing that signal itself, critically, without anyone telling you beforehand what it should be.
Okay, so like figuring out a language just by listening.
Kind of, yeah. Imagine you're in a really crowded, noisy room, and someone starts speaking a language you don't instantly recognize. AMC is like having this highly trained ear that, just based on the rhythm, the tone, the specific sounds, even the really subtle nuances, can tell you, okay, that sounds like English.
Hmm.
And then, maybe even more specifically, and that sounds like a particular regional dialect of English. It's basically deciphering the hidden code automatically.
That's a perfect illustration. So, okay, why does it matter so much? Why do we care if our devices can automatically identify these different accents? What are the real-world implications of AMC that, impact our daily lives?
Oh, it matters for several absolutely critical reasons. It truly impacts how efficiently, how reliably, and how securely our entire wireless world operates. Let's maybe break down some of the key applications.
Yeah, let's do that.
First, there's resource optimization. Picture the electromagnetic spectrum as this incredibly bustling highway, right? Every wireless signal is like a vehicle trying to get to its destination. Now, if you know the exact make and model, the modulation scheme of each vehicle, you can manage the traffic much more intelligently.
Makes sense.
Your device, or the network itself, can then optimize how it decodes that specific signal using the most efficient algorithms tailored just for that modulation. And this isn't just some minor tweak, it makes communication significantly more efficient. We're talking faster data speeds, more reliable connections, and ultimately saving invaluable network resources like bandwidth and power.
And for us, the users.
For you, the listener, this translates directly into smoother video calls, quicker downloads, and probably longer battery life on your devices. Without AMC, networks would basically have to guess or maybe try multiple decoding methods, which wastes time and energy.
So it's not just a guessing game. It's more like a digital traffic controller, making the most of every precious bit of signal.
Precisely. It's about maximizing throughput and minimizing waste in what is, after all, a finite resource. Secondly, AMC is vital for interference detection. In today's incredibly crowded airwaves, unwanted signals, whether they're from rogue devices, maybe faulty equipment, or even malicious jamming, can wreak absolute havoc.
Right, like someone shouting in that crowded room analogy.
Exactly like that. Imagine trying to have a clear conversation, but someone else is constantly shouting over you. AMC acts like a specialized sound engineer, able to pinpoint the source of that unwanted noise by identifying its specific modulation scheme. So if an unauthorized signal suddenly appears with an unusual or unexpected modulation, AMC can flag it immediately. And that allows the system to quickly take action to mitigate it, maybe adjust frequencies, change power levels, or even alert operators to a potential security threat or equipment malfunction. It helps keep our wireless conversations clear.
Okay, so resource optimization, interference detection.
But what else? Third, and this is increasingly important in our interconnected world, it serves as a really powerful security measure. Think of AMC as a highly discerning digital bouncer at a very exclusive club.
Okay, I like that image.
By continuously monitoring incoming signals and identifying their modulation schemes, AMC can detect and immediately block attempts to access a system using unapproved or unusual modulation types. This adds an absolutely critical layer of defense against unauthorized access or, malicious attacks. If some cyber attacker tries to infiltrate a sensitive communication network using a modulation scheme that's not part of the approved protocol, AMC can spot this anomaly, identify it, and help shut it down, often before any real damage is done. It's like a silent, ever-vigilant guardian of our digital communications.
Wow, okay. That's a big one.
It is. And finally, AMC contributes significantly to overall network capacity. By intelligently understanding and classifying these different signal types on the fly, wireless networks can be dynamically optimized to handle more traffic, reduce congestion, and minimize signal clashes. Think about that bustling highway again. If the traffic controller knows exactly which lanes are carrying fast-moving data, which are carrying voice, and which might be for emergency signals, they can allocate resources much more effectively.
So everyone gets a smoother ride.
Pretty much. It means more devices can connect simultaneously without degrading performance, and each device gets a better, more consistent experience. So really, every time you're making a video call on a crowded network, or streaming a movie in a busy coffee shop, or interacting with dozens of smart home devices, all of that seamless experience relies heavily on efficient spectrum use, and AMC is a key, often unsung, player in making that happen for you. It's truly the unsung hero enabling our ultra-connected lives.
That really brings it home. It's fascinating how something so foundational, so unseen, impacts our daily experience so profoundly. Now, if we look back in time a bit, how did engineers try to crack this modulation code in the past? before deep learning, this sort of new AI paradigm even entered the picture.
Right. Well, traditionally, the efforts to crack this code can be broadly grouped into a few stages, each with its own, merits and limitations. The earliest significant attempts were often based on probabilistic approaches. These methods used complex statistical models to try and infer the most likely modulation type based on the observed characteristics of the signal. For example, some early algorithms would try to classify things like BPSK and QPSK by comparing intricate log likelihood functions. Others focused on minimizing the difference between the received data's log likelihood and the expected log likelihood to improve performance.
Sounds complicated.
It was.
Yeah.
And while these were mathematically rigorous, kind of foundational, they really struggled as the number of different modulations in use rapidly increased. And critically, they struggled when signals became noisy. By noisy, we mean at lower signal-to-noise ratios, or SNRs, where the actual signal is barely distinguishable from the background electronic chatter. They were also often computationally very complex, demanding a lot of processing power, which made them really difficult to implement in real time or on, say, resource-constrained devices like mobile phones or small sensors.
So they worked in theory, maybe, but they weren't really scalable or robust enough for the chaotic, increasingly complex reality of wireless communication.
Exactly. They were kind of like trying to identify every single instrument in a massive chaotic orchestra by hand-tuning individual sound filters for each one. Accurate for a few instruments in a quiet room, perhaps, but completely overwhelmed by the full symphony. Then came traditional machine learning, or ML, approaches. These included algorithms you might have heard of, like naive Bayes, random forests, k-nearest neighbors, KNN, and support vector machines, SVMs.
Okay, familiar names. Were they better?
They were generally less computationally complex than the probabilistic methods, which was definitely a step forward. However, they often yielded lower classification accuracy, especially when you compare them to what deep learning can achieve today. But the biggest, most fundamental challenge for these traditional ML methods was their reliance on something called handcrafted feature extraction.
Handcrafted feature extraction. That sounds like a very human-intensive process. What did that actually involve for an engineer back then?
It meant that humans, the engineers, had to painstakingly analyze the signals and manually tell the system what specific aspects or features of the signal to look for. They'd have to calculate things like higher-order cumulants, which are complex statistical moments of the signal, or perform cyclic spectrum analysis, which looks for periodic patterns hidden within the signal. It was kind of like a master chef having to not only cook a dish, but also explain to the computer exactly how to taste each ingredient and what specific chemical compounds to look for to determine if it's sweet or savory.
Wow, okay. So incredibly time-consuming and requires deep expertise.
Exactly. It was incredibly time-consuming, required deep domain expertise in both signal processing and machine learning, and crucially, it was prone to missing the subtle, complex, and often nonlinear patterns that might be absolutely critical for accurate classification. It really placed a significant bottleneck on the system's ability to adapt and learn.
This is where it gets truly fascinating, isn't it? Because that manual feature extraction sounds like a massive, almost insurmountable bottleneck as wireless systems just kept getting more sophisticated. So when did the paradigm shift happen? What was the truly transformative aspect of deep learning that made it such a game changer for AMC?
The pivotal shift, the real breakthrough, came when deep learning, particularly fueled by its phenomenal success in things like image processing, computer vision, and natural language processing, started to be applied to signal processing. Traditional methods were, as you implied, like asking a human expert to draw this perfect map of all the important landmarks in a vast, unexplored territory before an explorer could even begin their journey. Deep learning fundamentally changed the game because of its incredible ability for automatic feature extraction.
Automatic feature extraction. That sounds like the key.
It is the crucial distinction, the real aha moment. Deep learning models, they don't need humans to handcraft these features. Instead, if you give them enough raw data, they can automatically learn and extract the most relevant, complex, and hierarchical patterns directly from the raw signals themselves. It's kind of like giving the AI a vast library of wireless sounds and letting it teach itself what distinguishes a voice call sound from a Wi-Fi data sound. This makes them far more efficient, incredibly adaptable, and remarkably accurate. They're capable of discovering these subtle relationships that humans, with all our inherent biases and limitations, might completely miss.
Okay, so that's a huge leap. But the paper we're looking at points out a limitation even with these early deep learning methods, right? This idea of a flattened problem.
That's right. Even with this monumental leap, the paper highlights a significant limitation of most existing deep learning methods used in AMC up to that point. They tended to treat all modulations, both the analog ones and the digital ones, as one big, flattened classification problem. They'd essentially feed all types of signals, from old-school analog radio to cutting-edge digital Wi-Fi, into a single monolithic model. And they expected this one model to somehow differentiate between, say, an analog FM radio signal and a complex digital 64 QAM Wi-Fi signal using the exact same internal logic for both.
So if I'm following that flattened approach was kind of like asking a single AI to be a master of all trades, trying to identify both a cat and a car using the exact same internal reasoning, even though they have fundamentally different characteristics and underlying structures.
Precisely. That's a great way to put it. That approach overlooks a fundamental truth. Analog and digital signals behave very, very differently. They have distinct characteristics, different mathematical properties, different physical representations. Trying to classify them all at once with one model can make the learning task unnecessarily difficult for that model. It's like training a doctor to diagnose every single illness in the world, from a common cold to a rare neurological disorder, with one single algorithm. It might theoretically work eventually, but it's incredibly inefficient and probably prone to errors because the underlying mechanisms are just so different. So this raises a really important question. Could we get better results? Maybe improved accuracy, maybe lower complexity, by respecting the inherent structure of these modulation schemes? Could we design a system that first recognizes the broad category and then specializes within it?
Okay, so if that flattened approach was like asking a single AI to be a master of all trades, how do these researchers tackle that fundamental limitation? What was their multi-level masterstroke that allowed them to approach this problem with, it sounds like, far more nuance and ultimately more success?
Ah, yes, that's where the real genius of this paper's core innovation lies. This hierarchical or multi-level approach. Instead of forcing one massive AI model to learn everything about all 10 modulation types simultaneously, they cleverly broke down the complex task into more manageable, specialized subtasks. It's a bit like a highly efficient sorting system, you know. The two main stages are:
Okay, stage one.
first, parent class classification. Here, the system takes any received signal and makes an initial high-level decision. Is this signal analog or is it digital? This acts as the primary filter, a crucial gatekeeper right at the very beginning of the process.
And stage two.
Second, subclass classification. Once that initial broad classification is confidently made, once it's identified as either analog or digital, then a completely specialized classifier takes over. So if it's flagged as analog, a model specifically trained only on analog signals will decide if it's AM-DSB or WB-FM. If it's flagged as digital, a different, highly specialized model trained only on digital signals will classify it among those 8 digital types like BPSK, QPSK, QAM, and so on. This targeted approach allows the deep learning models to learn and discriminate the unique, often very fine-grained features present within these distinct modulation families much more effectively. It leads to better overall performance and potentially better efficiency, too. It's really about specialization leading to mastery.
And to implement this clever multi-level strategy, the researchers proposed 3 distinct deep learning models, each with its own specialized role. Is that right? Can you walk us through them and maybe explain what each one brings to the table without getting us too lost in the weeds of, like, specific filter numbers?
Absolutely. These 3 models are the intelligent agents, you could say, forming the backbone of their multi-level architecture. The first one is the ADMC, that's the Analog Digital Modulation Classifier. This is our gatekeeper, the initial decision maker. Its sole purpose is to take the raw incoming signal, which comes in the form of what are called IQ components, and determine if it's fundamentally an analog or a digital signal.
IQ components. Remind us what those are.
Sure. Think of IQ components as the 2 essential streams of data, in phase and quadrature. Together, they capture all the necessary information about a radio wave, like its amplitude and its phase at any given moment. They are truly the fundamental building blocks, especially for digital radio.
Got it. So the ADMC looks at these raw IQ components. What's special about its design?
Its architecture is actually quite sophisticated. It includes 2 convolutional layers, or CNN layers. These are excellent for learning precise spatial features. Think of them like sophisticated pattern detectors that can identify specific localized characteristics within the signal structure, sort of like finding edges or textures in an image. These are followed by an average pooling layer. Imagine pooling is taking a sort of bird's eye view of the patterns the CNNs found, summarizing the most important information and discarding some redundancy. This helps the model focus on what truly matters without getting overwhelmed by too much detail. And it also makes the model more robust to minor variations or shifts in the signal. They also incorporate a batch normalization layer.
Hmm.
This is a really neat trick, common in deep learning now, that helps stabilize and accelerate the training process. It effectively reduces overfitting, where the model just memorizes the training data and helps it generalize better to new, unseen data.
Okay, so it's intelligently distilling the fundamental characteristics that differentiate analog from digital, making it robust.
Exactly. And because wireless signals inherently have this time-dependent nature they evolve, they change over a sequence, they've also cleverly integrated a long short-term memory, or LSTM, layer. LSTMs are specialized types of recurrent neural networks, and they're particularly good at recognizing time-dependent features, patterns that unfold over time in a sequence. This allows the model to essentially remember crucial temporal dynamics, which is vital for understanding how a signal changes over its duration. Think about the rhythm or cadence of a signal.
Right, the how it changes part.
Precisely. Finally, all these rich extracted features, both spatial and temporal, are fed into a standard fully connected neural network, or FCNN, which makes the ultimate decision.
Hmm.
The output layer uses something called a sigmoid activation function. This just converts the output into a probability, a number between 0 and 1, acting as a clear threshold for classifying analog versus digital. It's a really elegant and robust design for that critical first decision.
Okay, so once the ADMC has made that initial call, analog or digital, does that really simplify the problem enough for the next stage? Or are there still significant challenges even within, say, just the analog signals? How does the analog expert overcome those specific hurdles?
That's an excellent question, and it's precisely why this specialization is so key. Even within the analog domain, the signals can be deceptively similar. So if the ADMC classifies a signal as analog, the second model, the ANMC, or Analog Modulation Classifier, takes over. Its sole purpose is to distinguish between the two analog types in this particular dataset, AMDSB and WBFM. What's truly unique and interesting about the ANMC is its hybrid model architecture. It cleverly combines both CNN and LSTM layers, but uses them in parallel.
In parallel, how does that work?
So the CNN layers, once again, are busy extracting those precise spatial features from the signal. And strategically placed here is a dropout layer, which is another technique to prevent overfitting. It randomly drops some connections during training, making the model more robust and ensuring it generalizes better to new, unseen analog signals it hasn't encountered before. After the convolution part, there's a max pooling layer. This is similar to average pooling in that it summarizes information, but instead of averaging, it takes the maximum value. This helps capture the strongest or most prominent features detected by the CNNs. Now, in parallel to all that CNN processing, an LSTM layer processes the reshaped input specifically to capture the temporal features unique to these analog signals.
So it's essentially getting the best of both worlds simultaneously, parallel spatial analysis and temporal analysis, and then combining that richer information to make a much more informed decision. That feels very sophisticated.
It truly is. These combined features from both the CNN stream and the LSTM stream are then concatenated, essentially stitched together end to end to form a really comprehensive representation of the analog signal. These combined features are then fed into a final FCNN, and the last layer uses a softmax activation function. Softmax is a powerful tool often used for multi-class classification, even when there are just two classes like here. It provides a probability distribution over the possible outcomes, like saying, I'm 70% sure it's AMDSB and 30% sure it's WBFM.
Okay, makes sense. And then, of course, if our gatekeeper, the ADMC, determines it's a digital signal initially,
Then we have our other specialist waiting in the wings.
which I assume is our digital expert, the DMC, or Digital Modulation Classifier.
Exactly. If the ADMC says, this looks digital, this model steps in. Its job is to classify among the 8 different digital modulation types present in the dataset, things like BPSK, QPSK, QAM16, QAM64, and the others. Now, the architecture of the DIG-MC closely resembles the ANMC, again leveraging the combined power of both CNN and LSTM layers. However, there's a crucial, very thoughtful design difference here. Instead of just a single LSTM layer working in parallel with the CNN, it uses 2 parallel LSTM layers.
2 LSTMs. Why 2?
This is a really clever design choice rooted in the nature of digital signals. Digital signals often have those distinct in-phase I and quadrature Q components we mentioned earlier. These 2 components carry separate yet complementary information about the signal state. By giving each component, the I stream and the Q stream, its own dedicated LSTM layer, the model model can capture even more specific and potentially nuanced temporal features from both streams simultaneously. It's like having two ears focused on slightly different aspects of the sound. These separate LSTM outputs are then combined, concatenated again, with the CNN stream's output. This combined feature set feeds into a final FCNN, this time with an 8-node output layer using softmax activation, corresponding naturally to the 8 distinct digital classes it needs to choose from.
That's a very clever way to leverage the inherent structure of those digital IQ signals to extract more precise information. It really speaks to that idea you mentioned earlier, smart AI design, not just brute force complexity.
It absolutely does. And the overarching design philosophy for all three of these models wasn't just about throwing raw complexity at the problem, building the biggest, most computationally intensive neural network possible. It was clearly about achieving a parallel and deliberate balance between computational cost and actual performance. The researchers systematically tuned these models, selecting appropriate layers and hyperparameters, things like the number of filters or memory elements through rigorous experimentation. They explicitly mention starting with basic architectures and only adding depth or complexity when it demonstrably improved performance, while also using techniques like pooling layers to efficiently reduce dimensionality without losing critical information. It's really a testament to smart, efficient design, prioritizing practicality and deployability over just theoretical accuracy on paper. And that is absolutely critical for real-world applications where resources like processing power and energy are often very limited.
That makes perfect sense. You need something that actually works in the field, not just in a lab. So, okay, to train these sophisticated AI models, you need a substantial amount of high-quality data. We mentioned the researchers use something called the RML 2016.10b dataset. What does that actually mean for our listener? What kind of data is it, and why is it so important for training these deep learning models effectively?
Right. The RML 2016.10b dataset, it's truly a cornerstone for radio signal classification research, and a huge plus is that it's openly available, which is fantastic for the global research community, allowing others to build upon and compare results fairly. It's essentially a vast, meticulously curated collection of wireless signals that serves as a standard benchmark for training and testing these AMC models.
So what's actually inside it? What does the data look like?
It consists of those IQ samples we discussed, the raw in-phase and quadrature components of a signal. Imagine them as two synchronized streams of numbers that together perfectly describe the amplitude and phase of a radio wave at every given moment. These aren't just theoretical numbers, they are the fundamental building blocks of how digital radio signals are represented and processed by our devices. Each signal in this dataset is meticulously captured and represented as an IQ vector, which is essentially a snapshot of its behavior over a short period of time, like 128 time steps in this case.
And it covers a really wide range of languages or modulation types, doesn't it? You mentioned 10 types earlier.
It absolutely does, and this diversity is crucial for robust training. The dataset features a broad diversity of 10 specific modulation types. As we touched on, this includes 2 common analog modulations. AM/DSB, think older radio broadcasts or maybe citizen band radio, and WBFM, wideband frequency modulation, which is essentially what your traditional FM radio uses for clear audio. Then there are 8 distinct digital modulations representing a wide spectrum of modern wireless communication techniques. BPSK, binary phase shift keying, CPFSK, continuous phase frequency shift keying, GFSK, Gaussian frequency shift keying, PM4, 4-level pulse amplitude modulation, QAM16, 16 quadrature amplitude modulation, QMN64, 64 quadrature amplitude modulation, QPSK, quadrature phase shift keying, and 8PSK, 8 phase shift keying. This comprehensive range ensures the models are exposed to a wide variety of signal behaviors they might actually encounter out there in the real world.
And crucially, real-world signals are never perfectly clean, right? There's always background noise, interference. How does the dataset prepare the models for that messy reality?
That's a profoundly important point, and the RML 2016.10b dataset accounts for it brilliantly. It includes signals with drastically varying signal-to-noise ratios, or SNRs. Remember, the SNR is just a measure of how strong the desired signal is compared to the background noise level. This dataset ranges from extremely noisy conditions way down at -20 dB, where the signal is barely a whisper above the static, all the way up to very clear conditions at +18 dB, where the signal is strong and distinct. And these levels are provided in standard increments of 2 dB.
Okay, so from barely audible to crystal clear.
Exactly. And this is vital because, as you said, Real-world wireless signals are never perfect. They're always battling noise and interference from countless sources. Maybe it's atmospheric static, interference from other electronic devices nearby, or even just the inherent thermal noise generated by the electronic components themselves. Training models across this vast range of SNRs makes them incredibly robust and much more applicable to almost any practical scenario, from maybe a crystal-clear fiber optic link down to a very weak signal coming from a distant satellite.
And the sheer amount of data.
In terms of scale, the dataset is truly impressive. It contains a total of 1.2 million individual signals. To break that down, that's 6,000 unique signal examples for each of the 10 modulation types, for every single one of those different SNR levels, from nectar-bis 20 dB to plus 18 dB. This massive amount of data is precisely what allows these deep learning models to learn the complex, subtle patterns effectively without just, memorizing the specific examples they've seen.
And it's not just synthetic data, right? They tried to make it realistic.
Yes, absolutely. For realism, the researchers who created the dataset went to great lengths to ensure it wasn't just pristine, perfectly generated synthetic signals. They actually used real voice and text data for modulating the signals, making the information content itself representative of real communication. More importantly, they deliberately incorporated common real-world error effects that signals inevitably encounter in practice. This includes things like random walk drifting of the carrier frequency oscillators and the sample time clocks. Imagine a slight unpredictable wobble in the exact frequency or timing of the signal, like a tiny tremor in a clock's ticking. They also included time-varying multipath fading. This is where signals bounce off objects like buildings, hills, or even people, creating multiple copies of the signal path that arrive at the receiver at slightly different times, often causing the signal to fade in and out unpredictably. And of course, they added additive white Gaussian noise, AWGN, which is a common model for the general background electronic hum that's almost always present. So all this means the models are rigorously tested against scenarios you'd actually encounter out in the wild, not just in a perfectly clean, idealized lab environment. When these AI models perform well in this dataset, it gives us very high confidence that they can actually handle the messy, unpredictable reality of wireless communication.
Okay, that's a fantastic overview of the foundation. Now let's talk performance. Building these sophisticated AI models is one thing, but the real test is always how they perform in the messy reality of data. When the researchers put their initial gatekeeper model, the ADMC, through its paces, they immediately ran into a classic machine learning challenge, something called imbalanced data. Can you explain what that problem means in the context of our wireless signals and how they intelligently addressed it?
Yes, this is indeed a classic challenge in machine learning, and it was handled with considerable elegance here. The imbalanced data problem arose because the RML 2016.FANOB dataset, while comprehensive, had this uneven distribution of signal types. Specifically, as we noted, there were 8 digital modulation types for every 2 analog types. If you just look at the total number of signals, this created roughly an 80.10 Denny ratio. 80% of the signals were digital and only 20% were analog. Now, if you simply train a deep learning model normally on such imbalanced data, it tends to become really good at predicting the majority class in this case, the digital signals, but significantly worse at predicting the minority class, those analog signals.
Why does that happen?
Because from the model's perspective, mathematically, it can achieve high overall accuracy just by always guessing the majority class. It's like that weather forecaster we talked about who always predicts sunny days because statistically, most days are sunny. Their overall accuracy might look excellent, maybe 80% correct predictions on paper, but they're completely useless for predicting any rainstorms because they always miss them. Their 80% accuracy is fundamentally misleading because it doesn't reflect their inability to predict the critical but less frequent events.
That's a perfect illustration of how simple accuracy can hide a critical flaw. So how do they make the ADMC care about those rarer analog signals? How do they make it a truly useful gatekeeper?
They employed a combination of smart and actually pretty well-established solutions to counteract this bias effectively. First, they used something called initial bias. This is a small calculated adjustment that's applied right at the very beginning of the training process, specifically to the output layer of the model. It's sort of like giving the model a subtle hint from the get-go about the actual class distribution in the data. It essentially prevents it from getting stuck on predicting only the majority class during its very first few learning iterations. This helps the model's learning process, or its loss function, converge more efficiently right from the start.
Okay. So a little nudge in the right direction.
Exactly. Second, they implemented class weights. During the training process, the model is basically instructed to give more attention or weight to the errors it makes on the less common or minority class, those analog signals. This means that if the model makes a mistake predicting an analog signal, that mistake carries a heavier penalty, a larger cost in the training calculation, than a mistake predicting a much more common digital signal. This effectively forces the model to care more about getting the minority class right, even if it means potentially sacrificing a tiny fraction of its accuracy on the majority class. It's a way of balancing the scales of importance, even if the raw data itself is unbalanced.
That sounds like a very clever way of incentivizing the AI to be more, well, fair in its predictions across the board.
It is. And third, and this is critically important for evaluation, they used a special metric to evaluate the model's performance called balanced accuracy, BA. This metric directly addresses why simple accuracy, just the total number of correct predictions divided by the total predictions, can be so misleading with imbalanced data, like with our overly optimistic weather forecaster. Balanced accuracy explicitly takes into account both sensitivity, which measures how well the model finds the true positive cases, so correctly identifying analog signals when they are analog, and specificity, which measures how well it finds the true negative cases, correctly identifying digital signals when they are digital. It then averages these two scores. This gives a much, much truer picture of the model's real-world performance because it ensures the model performs well across all classes, not just the dominant one. It tells you if your weather forecaster can reliably predict both sunny days and rainstorms effectively.
Okay, so they tackled the imbalance head on. How did the ADMC actually perform with these adjustments?
With these intelligent techniques applied, the ADMC model achieved genuinely impressive results. On the held-out test dataset, it correctly predicted analog modulations with 86% accuracy and digital modulations with 92% accuracy. This translates to an overall balanced accuracy of 88.8%. What's particularly striking is its performance across different noise levels, the different SNRs. For signals with SNRs above 9010 dB, which is still quite noisy, mind you, significantly challenging this model accurately identifies whether a signal is analog or digital over 98% of the time. That's incredibly precise for a gatekeeper, especially given the noise. It means this initial filter is performing exceptionally well, really setting the stage perfectly for the next, more specialized classification levels.
Okay, so the gatekeeper works exceptionally well, proving its value. That's great news for the first step. But once that initial classification is made, what about the specialized experts for the analog and digital signals, the ANMC and the DIG-MC? How did they perform once the initial sorting was done, and did they face their own unique challenges within their specific domains?
Let's certainly dig into that. Because even after the ADMC performs its remarkable initial split, the subclassifiers definitely face their own sets of nuanced challenges. Let's start with the ANMC, the Analog Modulation Classifier. This model achieved an overall testing accuracy of 62.5%. Now, while this might seem notably lower than the ADMC's impressive numbers at first glance, the researchers highlighted a very important and inherent characteristic of the analog signals themselves in this dataset. The IQ components of AM/DSB and WBFM, when you visualize them, look remarkably, even deceptively similar. They share fundamental visual characteristics when plotted in what's called a constellation diagram. This makes them inherently difficult to distinguish, even for experienced human experts looking at the plots. Imagine trying to tell apart two identical twins when you can only see slightly blurry photos of them.
So it's partly the nature of the signals themselves being tricky.
Exactly. It's a genuinely tough classification problem due to the intrinsic properties of the signals, not necessarily a fundamental limitation of the AI model itself. The maximum accuracy for this ANMC model was observed at 71% at a 4 dB SNR, which indicates its best performance comes with cleaner signals, as you'd expect. But that inherent similarity remains a significant hurdle. This suggests there's still perhaps scope for improvement in differentiating these very subtle analog differences in future work, but it clearly highlights an intrinsic real-world challenge rooted in the signals themselves.
It's like trying to tell apart two very similar shades of blue, maybe, even when we have good lighting. You might get it right most of the time, but it's still inherently a struggle.
That's a great analogy, exactly. Then we have the DIG-MC, our digital modulation classifier. This model achieved a slightly better overall testing accuracy of 66%. This model, while powerful, also faces its own unique set of challenges, mostly related to how digital information is encoded onto the signals. For instance, some specific digital modulation types like 8PSK, QAM16, QAM64, and QPSK actually share common constellation symbols. These symbols are like their unique fingerprints, the distinct patterns they form when their IQ components are plotted on a graph. Because these patterns can overlap or be very close geometrically for different modulation types, especially as signals become noisier, it makes them tricky for the model to reliably tell apart.
Can you give an example of the confusion?
Sure. The paper notes, for example, that about 16% of the true QAM64 signals were misclassified by the model as QAM16. And this makes perfect sense if you think about their structure. QAM16 is essentially a subset of QAM64 in terms of its symbol structure. QAM64 has more possible symbol states, but some of those states will look identical to or very close to QAM16 states, especially with noise. It's a bit like trying to tell if a photograph is of a family of 4 or a family of 8 when you can only clearly see the 4 people in the front row.
Gotcha. So inherent ambiguities there too. But how did it do with cleaner signals?
Well, the DIG-MC shows very strong performance at higher SNRs, which is encouraging. For cleaner signals, specifically those with SNRs higher than -2 dB, the model achieved over 94% accuracy, and it reached a peak performance of 97% accuracy at 10 dB SNR. This means when the signal isn't buried deep in noise, the digital expert truly shines, showing its remarkable capability to discern very subtle differences when the information is clearer and less corrupted by interference.
So this really shows you the nuanced challenges even these advanced AI models face. Sometimes the signals themselves are just so inherently similar or overlap in certain ways that it takes incredibly fine-grained analysis to tell them apart. It's almost like trying to distinguish between nearly identical twins when maybe one is just a slightly blurrier image of the other.
Yeah.
It really puts the complex problem, doesn't it?
It really does. It highlights that while AI is incredibly powerful and can learn patterns far beyond direct human comprehension sometimes, it's still ultimately operating within the physical limitations and inherent ambiguities of the signals it receives from the real world. It can't magically invent distinctions that aren't really there or are obscured by noise.
All right, so we've got a brilliant gatekeeper in the ADMC and two highly specialized experts, the NMC and DIG-MC, each doing their best with tricky signals. When you put all three of these specialized models together, working in concert as a complete system, how does this multi-level deep dive actually perform overall? What's its total effectiveness, and importantly, how does it stack up against the competition in the highly competitive world of AI research for AMC?
Right. Integrating the trained ADMC, NMC, and DIG-MC models into that single cohesive multi-level classification system, the overall accuracy achieved across all 10 classes and all SNRs was 63%. Now let's break that down a bit for context because the average doesn't tell the whole story. At a higher SNR of 10 dB, where the signals are quite clear, the system's maximum accuracy reached an impressive 91.93%. And the really good news here, from a practical standpoint, is that for SNRs of 2 dBs or higher, which represents a reasonably clear, usable signal environment for many real-world applications, the complete multi-level model consistently achieves over 90% overall accuracy. That's a crucial threshold for many practical deployments, as it signifies very reliable performance when the signal quality is decent.
Okay, so strong performance when the signal isn't too noisy. Where did the errors tend to happen?
We should definitely acknowledge where the challenges persist. As you'd absolutely expect, most of the misclassifications occur at the very low SNRs, where the signal is heavily corrupted by noise. At those levels, distinguishing modulation types is incredibly difficult, even for human experts or theoretical optimum classifiers. Additionally, some of the misclassifications involving the analog types, AMDSB and WBFM, stem directly from that initial, albeit small, misclassification rate by the ADMC model, our gatekeeper. If the gatekeeper mistakenly sends an analog signal down the digital path, which happen about 10–14% of the time, depending on the signal, it will almost certainly be misclassified by the digital expert, DIG-MC, regardless of how accurate that digital expert is on actual digital signals. This just illustrates the potential for cascading errors in any multi-stage system.
Right, an error early on can propagate. But you mentioned earlier there was a significant breakthrough for analog modulation, specifically with this model, didn't you? Something that other models struggled with.
Yes, absolutely. This is a very big win highlighted in the paper and a key advantage of their approach. For the analog modulation specifically, the proposed multi-level model gives more than 68% accuracy at high SNRs, like 18 dB. Why is this important? Because previous state-of-the-art methods typically only achieved high accuracy, usually over 70%, for one of the analog modulations, but not for both simultaneously. They often excelled at classifying, say, AM-DSB, but then struggled significantly with WBFM, or perhaps the other way around. This new multi-level model, because it has that dedicated NMC expert, is significantly better at learning the distinct features from both analog classes. It offers a much more balanced and robust classification performance for analog signals overall, rather than implicitly prioritizing one over the other due to limitations in a single flattened model. It means the model doesn't just get lucky lucky with one analog type. It seems to genuinely understand and effectively classify both, which is a real step forward.
That balanced performance is key. And did they do anything to check if these results were reliable or just maybe a lucky fluke with how they split the data?
They absolutely did. To ensure the model's reliability and its ability to generalize beyond the specific data split they used for testing, they also performed cross-validation. This is a critical technique in machine learning where you rigorously test the model's performance on different random splits of the dataset. Often this is done by using different seed values when shuffling the data before splitting it into training and testing sets. It's kind of like reshuffling the deck of training and testing cards multiple times to make absolutely sure the results aren't just a fluke of one particular arrangement of the data. The fact that the performance remained remarkably stable across these different random sets, for example, the ADMC showed balanced accuracies of 87.67%, 80.0%, 86.60%, and 87.34% across 4 different seeds is a very strong indicator of the model's robustness. It shows it can generalize effectively to unseen data variations. This consistency builds immense confidence in its potential practical utility.
And what about pushing the boundaries even further? Did they test it on newer, perhaps even more challenging data sets that represent even messier real-world scenarios than the 2016 dataset?
They absolutely did, which really demonstrates a strong commitment to evaluating real-world applicability, not just performance on one standard benchmark. They also evaluated their trained multi-level model on RML22, which is a newer and generally considered more realistic dataset. RML22 is specifically designed to simulate severe fading scenarios. Imagine your Wi-Fi signal constantly bouncing off walls and objects in a really chaotic way, causing extreme and rapid signal degradation. It also incorporates even more complex real-world artifacts and channel distortions than its predecessor, RML 2016.0b. It's truly a tough proving ground for any AMC algorithm.
And how did it do on that tougher data set?
While the overall performance on RML22 was, as expected, slightly lower, they reported 59.93% overall accuracy. It's crucial to understand that this isn't really a failure of the model architecture itself. Instead, it's a vital indicator that for these truly extreme real-world conditions, like deep urban canyons with lots of signal reflection or highly mobile environments with fast-changing channels, future AI architectures will likely need to be specifically tailored and perhaps even more robust. They might need different features or layers designed explicitly for those harsher conditions. It signifies that research in this field is an ongoing journey of refinement and adaptation, constantly pushing the envelope to handle the relentless complexities of the real airwaves.
This all sounds incredibly impressive, especially the balanced performance and the efficiency. But how does this new multi-level model truly compare head-to-head with other cutting-edge AMC methods out there? Are we really seeing a significant leap, especially when you consider the practical implications of deploying these systems in the real world, like computational cost?
This is where the true competitive edge of this multi-level model becomes undeniably clear, and it really highlights a critical insight for AI development across all fields, not just wireless. The researchers directly compared its performance against several other established state-of-the-art or SOTA AMC methods. These included popular deep learning architectures like standard CNNs, referred to as CNN1 and CNN2, a CLDNN, convolutional long short-term deep neural network, and a combined CNN LSTM model similar in spirit but architecturally different. And the results are quite compelling. In terms of raw accuracy, the proposed multi-level model generally outperforms these other methods for SNRs above 0 dB. Remember, that's a crucial threshold for many practical applications where signals aren't perfectly clean but are still very usable. Even at lower SNRs, specifically in that challenging range of -8 dB to 0 dB, its performance is shown to be comparable to or even superior to the best alternatives, particularly the CNN LSTM model they compared against. The CLDNN model, while showing some competitive performance at very low SNRs, falls significantly behind at the higher, often more practical SNRs.
Okay, so accuracy is good, often better. But what about the complexity? You hinted that was the real kicker.
Exactly. This is where the aha moment really deepens, and it's all about the trade-off between complexity versus performance. While some of those other SOTA models might achieve similar accuracy in certain regimes, for example, the CNN LSTM model's peak accuracy was only about 1 percentage point different from the proposed model's peak. They achieved this performance at a much, much higher computational cost.
So it's not just about getting the right answer, but getting it efficiently. Perhaps even enabling deployment on less powerful hardware.
Precisely. And the efficiency gains demonstrated here are massive, directly impacting real-world deployability in a huge way. Let's look at the specific numbers they reported because they really tell the story powerfully. The proposed multi-level model has an astonishing 86.49% fewer trainable parameters than the comparison CNN LSTM model. To put that into perspective, trainable parameters are essentially the knowledge bits stored within the neural network. The more parameters, generally the larger the model, the more memory it needs, and the more computational power it demands to run predictions. So a reduction of almost 87% means the proposed model is dramatically smaller and lighter computationally.
Wow, 87% smaller. That's enormous.
It is, and this directly translates into profound practical benefits. Because it's so much smaller, it requires 58.33% less training time to reach its optimal performance compared to the CNN LSTM. And perhaps even more importantly for deployment, it requires 20.78% less testing time once trained and running inference in the field.
That's a huge difference. What does that mean practically?
It means everything for deployment. Imagine trying to implement these AI models in the real world. Maybe you have a sensor on a remote oil rig that's powered by a small battery, or a drone with very limited onboard computing power, or perhaps an Internet of Things device that needs to run efficiently for years on minimal energy. In those scenarios, a model that is nearly 87% smaller and trains and runs significantly faster is an absolute game changer. It means the proposed model can run effectively on less powerful, cheaper, and lower energy hardware. It makes advanced AI like this far more practical and economical for real-world applications, especially in these resource-constrained environments. The researchers explicitly state they achieved this remarkable low complexity by starting with a basic architecture and systematically adding depth only when it significantly improved performance, and by effectively using those pooling layers we discussed to reduce dimensionality without sacrificing key information. It's really a testament to smart, efficient engineering design, emphasizing surgical precision over just brute force processing power.
That's such a critical distinction for actually getting these advancements out of the lab and into the real world. You don't want a brilliant theoretical solution that requires a supercomputer to run it in every practical scenario. This sounds like it bridges that gap beautifully.
It absolutely does. Ultimately, this proposed multi-level model seems to strike the best, most practical balance among all the methods they analyzed. Superior classification performance, particularly in key SNR ranges, while maintaining remarkably moderate computational complexity. It's a significant and, I think, very practical step forward for the application of AI in wireless communication systems.
So what we've really seen today is a truly brilliant example of how targeted AI design, smart architectural choices, can tackle these incredibly complex, real-world problems effectively. By intelligently breaking down the automatic modulation classification task into more manageable, specialized steps, first distinguishing analog from digital signals, and then classifying the specific types within those broad categories, these researchers have genuinely pushed the boundaries of both accuracy and efficiency in decoding the invisible language of our wireless world. You've hopefully now got a much deeper understanding of why automatic modulation classification is so vital for our increasingly connected world, the really smart ways AI is being applied to solve these intricate challenges, and how innovative approaches like this multi-level architecture can make a profound difference in handling that unseen symphony all around us. It's truly about making the invisible, understandable, and ultimately manageable.
And perhaps if we connect this to the bigger picture, just as a final thought. Consider that while this deep dive focused primarily on classifying signals originating from a single source, the real future of wireless communication involves ever more congested airwaves. We're talking about billions of devices, all potentially transmitting simultaneously, with signals from countless sources, often overlapping, interfering, and interweaving with each other in incredibly complex ways. This raises a really important and challenging next question. How will AI evolve to untangle these overlapped signals from multiple sources? How can it act not just as a single-source whisperer, like we discussed today, but as a full-blown orchestrator, capable of identifying, separating, and understanding the entire wireless symphony at once, even when multiple instruments are playing conflicting notes simultaneously?
Wow, yeah. That sounds like the next frontier.
It really is. That's a challenge that will undoubtedly require even more clever deep learning architectures, perhaps entirely new paradigms for signal processing, constantly adapting to the growing demands and the increasing chaos of our incredibly connected world. It's an exciting space to watch.
Fascinating indeed.
Yeah.
A great place to leave it for today. Thank you so much for joining us on this deep dive into the truly invisible but absolutely critical world of automatic modulation classification. Until next time, keep that curiosity sparked.